All right, so now we're going to carry on with our discussion of derivatives, and we'll be looking now at some more complex rules. You can see for yourselves right there. We're going to, in this section, look at the product and quotient rules, and then we'll introduce the concept of higher order derivatives, because you can apply differentiation to a function as many times as you need to, although in practice, you usually don't do it more than 2 or 3 times, but you never know. Luckily, the rules are repeated each time you take a higher order derivative. So it's nothing terribly involved. It's just that we do need to know how they work. So anyway, we'll start with the product rule. Now, I mentioned before that unfortunately, the derivative of a product of functions is not equal to the product of the derivatives. That would be very nice, but that's just not the way it works. So here is the way the product rule works. Let me just copy it into the notes. All right, so you can see what's happening here is you're taking the first function and multiplying by the derivative of the second function, and then to that you add the second function times the derivative of the first. All right, so now this is one of those things that you really should memorize because you'll need it so often that, you want it to become second nature. So here's a good example of this. Let's just copy this. All right, so let's just say h of x is defined in the following way. We can write this as f of x, this is g of x. And now using the rules that we learned in the last section, we can figure out for ourselves that if f of x equals 3x minus 2x squared, that means that f prime of x, based on the power rule, must be 3 minus 4x. And then similarly, if g of x is 5 plus 4x, then g prime of x is simply 4. Now we plug these in to our rule, and we'll have a result. Okay, so the derivative, or we could write it in this case as h prime of x, is going to be f of x times g prime of x plus g of x times f prime of x, which, as you can see up here, is 3 minus 4x. Okay, so now we can do a little algebra and simplify our results. So what do we have here? Well, we have to distribute this 4 across these two terms. So we'll have 12x minus 8x squared. Now here, if I multiply these out, let's see, I can use FOIL. Get my result. All right, here we go. Here's F O I N West negative 16x squared. So when you bring these all together, you end up with 15 minus 8x minus 16x squared. So that would be this second part of our expression. So put it down here since I'm running out of space. 15 minus 8x minus 16x squared. And now we can gather up the like terms. We have one constant. Here we have 12x minus 8x, which is, of course, 4x. And then with these two, give me minus 24x squared. And that's the final result. Or, by convention, we normally, well, all right, let's do this. Normally you try to write them in descending order of exponents. In other words, while this is correct, let's rewrite it. And now we're all set. All right, now, here we go. We've got signs involved here. So don't forget the derivative of the sign is the cosine, and the cosine is the negative sign. So what do we have here? Oops. All right. So now that means in this case, if we think of this as h of x equals g of x, f of x times g of x, f of x would be the 3x squared. F prime of x, based on the power rule, would be 6x. G of x is sine x. And g prime of x is cosine x. Right? So remember, the rule is f of x, g prime of x, plus g of x, f prime of x. All right, so now we just substitute. Well, that's interesting how that turned out. Oh, no, sorry. I copied the wrong thing. This is 6x. I knew something wasn't right. All right, and then we can rewrite it slightly. I mean, let's just write it as 3x squared cosine x plus 6x sine x. And we're good. Okay, so they factored out the 3x, but we got the same thing, of course. Now, the quotient rule is even messier than the product rule. All right, what are you going to do? You know, some of these rules are quite complicated. So here's how this one works. With the assumption that g of x is not zero, of course, here's how we calculate the derivative of a ratio of two functions. All right, so we have g of x, f prime of x minus f of x, g prime of x. And then here we have to divide by g of x squared. Again, this is one of those rules that you'll probably want to commit to memory because you'll see it all the time. All right, let's try this one. All right, so what you could do is write this as h of x, f of x, or g of x. And in this case, that means that f of x is 5x minus 2. F prime of x is 5. G of x is x squared plus 1. And then finally, g prime of x will be 2x. So the rule tells us that h prime of x is g of x, f prime of x, minus 5x minus 2, that's f of x. G prime of x is 2x, all divided by x squared plus 1 squared. Don't forget about the square. Okay, so we can simplify this a little bit. Not much. So here we're going to have, so let's, in order to avoid any sign errors, let's first multiply 2x by this expression 5x minus 2. So we'll have 10x squared minus 4x. And so this leaves us with 5x squared plus 5 minus 10x squared plus 4x all over x squared plus 1 squared. All right, and then there's a couple of terms we can combine here. We've got minus 5x squared plus 4x plus 5, all divided by x squared plus 1 squared. Now, it's possible in these cases that you could evenly divide the denominator into the numerator, or there might be a common factor, but it doesn't look like it here, so we can just leave it like this. And you can see it is a very complicated rule. All right. So, oh, I see. See, what they're trying to do here is they're basically showing you why they're trying to prove why the power rule works using the quotient rule. Okay, so it's kind of interesting, I guess, but what they're trying to get at here is that k is some negative exponent. And when you derive this, you're going to end up with the power rule nx to the n minus 1, assuming that n equals negative k. I don't know how important this really is, but sometimes it's interesting to see how these results were derived. And of course, this is our old friend, the power rule. Never forget that one either. Trig functions. Now, we started to do this earlier. We only got to the sine and the cosine. So there probably is, I'm sure there's a website somewhere where we can just have a list right in front of us. Let's go find it. You can memorize these if you want to. I'm not sure if it's really all that important. And at least you should probably remember the derivative of the sine and the cosine. Um, these others actually are derived from these first two anyway, based on their definitions, but this is the complete list. And so they're going to give us a few examples. For example, we have y equals x minus tan x. So how do you calculate the derivative there? Well, this one is not going to require any rules, any complicated rules. All we're doing is taking the derivative of x and the derivative of negative tan x and combining them. So dy dx will be 1 minus, and again, the derivative of the tangent of x is the secant squared of x. And that's it, we're done. Okay. Now, this one's going to be fun because this one clearly does require the product rule. All right, so we have y equals x secant x. So again, you can think of this as h of x equals f of x times g of x. And here f of x is x, which means that f prime of x is 1. That's one of those special cases. Remember, the derivative of a constant is 0 and the derivative of x is 1 based on the power rule. And then that means that g of x is the secant. And once again, we may as well go consult with our chart. And not that chart. The derivative of the secant is tangent times secant. All right, so assuming we remember how this rule works. Let's make some substitutions and we'll get our answer. Okay, so we'll have x, tan x, secant x, plus secant x times 1. And, you know, they'll probably factor this out. So let's do that. And that's it. And we're finished. Yeah, they factored it out. Secant x times 1 plus x tan x. All right, beautiful. So while the rules are more complicated, they're not really difficult. It just takes just a little practice to get used to them. Higher order derivatives. I started to allude to this earlier. You're basically just repeating the same rules when you take higher order derivatives. Let me just show you a few examples before we start looking at the physics here. Oh, actually, before we even do that, let's look at the notation. I just realized that's coming up next. Here it is. So remember before we saw there's so many ways of expressing the first derivative, as it's called. Now you can see here, actually, let me copy this into the notes. So if you're using, for example, y prime is your first derivative, then you just add more primes. Although after you get to 3, we normally, to avoid confusion, we don't want to have a bunch of, accents there, I guess. So we write it like this. And then same thing with f prime. After you get to 3, we usually start writing actual numbers. The derivative dy, that it's different. You can just put the integer there. So d dy. The thing that's surprising though is that the second derivative is written like this. d squared y dx squared. Okay, and then from then on, you can see the third derivative is d cubed y dx cubed, et cetera, et cetera. And then these, the ones that we don't see as often, you can see the twos, the threes. That tells me the order of the derivative. So again, as always, we'll use whichever one is the most convenient. The idea here, though, is that the higher order derivatives are just derivatives of the derivatives. Okay, so now I'd like to show you a couple of simple examples of this. If f of x, for example, is 4x to the fifth, based on the power rule, f prime of x will be 5 times 4x to the fourth, 20x to the fourth. F double prime of x will be dx cubed. The third derivative, so it just keeps going on and on. Now, eventually you'll reach a point where it becomes zero. Okay, because at some point this will be reduced to a constant, at least if you started out with a polynomial. For some of the others, like the trig functions, it doesn't work that way. They'll rotate back and forth between different values, but for polynomials, actually, I just realized some books, you notice how I wrote this Roman numeral here. Some books use Roman numerals when you get to the really high order derivatives. I kind of like that notation, so I'm going to stick with it. And then f to the fifth derivative is going to be 480. And of course, that means that the sixth derivative, 0. Okay. Now, for practical applications, for all practical purposes, let's say, it's extremely unusual that we need derivatives higher than the second order. It's not impossible, but it's extremely unusual. Most of the time, we'll be working with the first or the second derivative. But it's important to know how to calculate all of them. So let's see what examples they have for us. Okay, now this is the physics one. S of t, the position. Let's do this one. Oh, what the heck? I'll just copy it. And while we're at it, let's grab the graph. Of course, you notice because this is a physics application, we don't need the other quadrants. Only the first quadrant is relevant. And they would like to remind us here, they did a couple of slides ago, that the velocity is the first derivative of the position, which is s. Okay. And then acceleration is defined as the second derivative. Actually, the first derivative of velocity, which implies that's the second derivative of the position function. So what they'd like us to do is calculate all three of these. So if s of t is negative 0.81 t squared, then the velocity will have to be negative 0.81 times 2t plus 0 or minus 1.62t. And then acceleration is v prime, which is minus 1.62. Okay, and that's all there is to it. I think this is one of those areas where physics is very helpful. I mean, or it's very useful for coming up with examples here because there's obvious interpretations of first and second derivatives here. So yeah, so it's negative 0.81 t squared plus 2. The velocity is negative 1.62 t, and then finally the acceleration is negative 1.62. All right. Now they're also telling us that, okay, what is the ratio of Earth's gravitational force to the moon's? Huh. Well, I don't know where they got that from. I guess we'll have to take the word for it. S double prime of t is negative g, the gravitational constant. And that's, of course, different on every planet and on every moon throughout the solar system. So it looks like it's the ratio of 9.8 to 1.62, because, of course, on the moon, there's hardly any gravity. All right. So now we're ready. Let's do another example of the product rule. By the way, I do want to point out here, though, that if you felt so inclined, you could just multiply these out and then apply um, the first derivative to each term in the resulting polynomial. But it probably would take a lot more time to do it that way. So, the thing is about these derivatives is that there's nearly always multiple ways of getting to the same result. You just have to choose the approach that is the quickest and maybe the easiest if it's possible. So let's rewrite this as h of x is f of x g of x. And that means that f of x is x to the fifth minus 3. F prime of x is 5x to the fourth. That means that g of x is x cubed plus 3, and g prime of x is 3x. So product rule, of course, is this. All right, and then we just make our substitutions. And that gives us x to the fifth minus 3, 3x squared. Okay, now I noticed in the answers that they multiplied these out and consolidated all the terms, so we'll do that here. I'm going to distribute this across both of these and here. So I'm going to get 3x to the 7 minus 9x squared plus 5x to the 7th plus 15x to the 4th. So there's two terms that have an exponent of 7. So I'll consolidate those right now. And there we go. All right. So that would be the last one. 8x to the 7th plus 15x to the 4th minus 9x squared. Beautiful. All right. And then here's an example of the quotient rule. Let's try that. So think of this again as h of x is f of x over g of x. And that means here f of x is the numerator, which is x plus 4. F prime of x is 1. G of x is x squared plus 9. And g prime of x is 2x. All right, and then the quotient rule is all right. So again, you really want to consider memorizing it. After you've used it enough times, you'll have it memorized anyway. But you can always look it up if you have to. I mean, especially in an online course, if you were in the classroom, there's certain things you would have to memorize. And you should probably anyway, because your next math class will be likely in the classroom. So think about it. Okay. So, all right, let's do some substitution. And then we have to divide by x squared plus knots. Okay. So we'll simplify it as much as we can. So, you know what, let's do this. Again, to avoid mistakes, let's first multiply these out before we apply the negative sign. Because, you know, it's so easy to make sign errors with something like this. All right, now we can drop the parentheses. And then let's see, we can consolidate a few of these terms. These two give me negative x squared minus 8x plus 9. And then we have this in the denominator. I don't think there's any way we can simplify it any further. So what do they have here? Looks like it's b minus x squared minus 8x plus 9 over x squared plus 9 squared. Beautiful. All right. So that, wow, that was fast. That was 2.3. What do they have in 2.4? The chain rule. Okay, now we're getting into some extremely deep waters. This is something that it can be very confusing. We need to really practice with this and get it straight because it's easy to make mistakes with it. And so what is this all about? Well, first things first, it's based on the concept of a composite function, meaning f of g of x. Okay, so in other words, why don't we go back and quickly review what we mean by a composite function? What if we had, for example, f of x is 2x, and g of x is x squared plus 1. Then f of g of x, which sometimes you see written like this, means what you're basically doing is you go to your f of x function, wherever there's an x, you replace it with g of x. Okay, so in this case, that would give us 2 times g of x. Okay. And then we just replace the g of x with its definition. And then, you know, I guess we can multiply it out. And then we can do the reverse. We can define g of f of x. Sometimes you see it written like this. And that means we go to the g of x function and replace all the x's with f of x. That's going to give us f of x squared plus 1. All right. Now, by the way, you can also have a composite function of a function with itself. Okay. You could, for example, have this. It's wherever there's an x, you're going to replace it with f of x. And the same thing with the g. So we've got g of x squared plus 1. And then you replace that with its definition. And then you can multiply it out if you want. Another interesting thing is that you can have as many composites as you want. In other words, you can actually define f of g or f of x. There's all kinds of things you can do. In other words, there's no limit to how many composite functions you can have. So the chain rule is based on a composite function. So let's see, what are they doing here? On the left, we have y equals x squared plus 1. Okay, now let's look at these two cases and see why. The one on the left doesn't require the chain rule. The one on the right does. All right, so here we go. Oh, and by the way, let us formally define the chain rule. They should have it here somewhere. There it is. Now, by the way, as always, there's different ways of doing this, but notation wise, there's a couple of approaches, and you might find that you might find one more easier to understand than the other. Okay. So we'll see about doing them both as we go along. And so you can see what they're basically telling us here is that if we have a composite function, f of g of x, the derivative of that entire expression is f prime of g of x times g prime of x. All right, so when you see a few examples, you'll start to get a sense of how this works. So the first one they give us, um, okay, so this one we don't need the chain. We know how to do this. End of story. What's different about that case and this case on the right? Y equals the square root of x squared plus 1. Because going on behind the scenes, we could think of this is our g of x, then f of x is x to the 1/2 power. So in other words, if x is f of x is x to the 1/2 power, or the square root, and g of x is x squared plus 1, then f of g of x means we substitute g of x wherever there's an x in our f of x, and therefore we have so in other words, it may not be super obvious, but this is a composite function. This is not. So we can just go ahead and use the power. This is a composite function, and we must use the chain. Now, there's a couple of ways we can do this. But here's one popular way of taking this expression and breaking it up into simpler pieces using differentials. So I'm going to show that to you because I think you'll find it to be easier than what you're seeing here, although we could certainly use this approach. But I'm referring to this over here. Okay, what is this all about? So we'll start again. So let's define u to be x plus 1. All right, that means that du dx is just 1. It also means that this function is nothing but u, radical u, okay, and dy, therefore dy du, or let's write it like this. Actually, it'll be simpler this way. So if you look at this definition, we need two things. We need dy du, which means 1/2 u to the minus 1/2 power. And then we need du dx, which is 1. Well, it just sort of worked out that way. And so according to what we're seeing here, the chain rule tells us that we have 1/2 u to the minus 1/2 power times 1. But we're not done because we need to replace that u with the definition x plus 1. All right. Now, let's just say you're not convinced that you did this correctly. All right. So we're claiming that the derivative is 1 over 2 radical x plus 1. Um, you could try this approach, but it's going to work out exactly the same. So let's just see what they have. Oh, it doesn't look like they went through all the steps. All right, well, but that is the right answer. Okay. Now, again, here you can see, now this is different. Um, Sine of x, sine 6x. Okay, because, well, all right, well, let's take a look at them. By the way, I do want to mention one of the reasons why you might want to get used to this notation here is because if you look in your book, there's a table, a massive table somewhere in there with a lot of these results, and they tend to use the letter U for their for these tables. So once you get comfortable with that notation, it should be very helpful in this class and especially in Calc 2. So let's see, what are they doing here? 6 sine y equals sine x and 6 sine 6x. All right, well, that was easy. Now, what's going on here with this one? Okay, so why don't we do this? Let's think of u as this right here. 6x u dx is 6. And then that means that y is the sine of u, and dy du is the cosine of u. All right, so the chain rule tells us that the derivative dy dx is dy du dx, which means cosine u times 6 cosine u, 6 cosine 6x. Uh-huh. See, so the derivative of sine x by itself is just the cosine x, but because this sine is a function of another function, in this case, you could think of sine of x as f of x, and then g of x is 6x. F of g of x is therefore sine 6x. And therefore, we must use the chain rule. And again, you could use the other notation if you prefer, which is that, let me just go, it should be right here. Let me go get a copy of it. So the derivative of sine 6x now f prime of x, in this case, you're going to get the sine, cosine rather, of 6x times g prime of x, which is just 6. Okay, so you can use either approach. I don't know about you, but I like the dy dx part. I mean the du dx over here. I just find that it's simpler. But it's up to you to decide which type of notation you want to use. Okay. So now here's a good example. Y equals 3x plus 2. There's no need to use the chain rule. There, you don't have a composite function. So we'll just use the power rule. But this one, 3x plus 2 to the fifth, you certainly do have a composite function because you can think of this as your g of x. And then f of x would be x to the fifth. So f of g of x would be g of x to the fifth. And that's your 3x plus 2. Okay. Or you could think of u as 3x plus 2, du dx is 3, and therefore, and y is u to the fifth. Therefore, dy du, based on the power rule, is 5u to the fourth. And so dy dx, which we know is dy du dx, is 5u to the fourth times 3, or all right, hold on. Everything got moved. And then we make the proper substitutions. That's your final result. Okay, so like I said, this one is a tricky one. Okay, so in other words, we'll need a lot of practice. All right, what do we have? So here they're kind of breaking it down a little bit and trying to help you understand the relationship between the different types of notation here. Um, yeah, so here they're showing you for the first time actually how to use the du dy dx setup. So if you've got y equals x squared plus 1 cubed, you can think of it as x squared plus 1. So y is u cubed. And so du dx is 2x, dy du is 3u squared. So therefore, and since u is defined as x squared plus 1, and then you can simplify, usually simplify whenever possible. So you end up with 6x times x squared plus 1 squared. Okay. Now, the general power. So all of this gives us the following important result. Now, the regular power rule that we saw earlier is very simple. What we're seeing here is more involved because instead of x raised to the n, it's u of x raised to the n. Okay. And so that means that we need to use the chain rule, and we end up with this result. That's the distinction between the two cases. The second case does require the chain rule. The first one does not. All right. So let's see if we can come up with some examples. All right, here we go. F of x equals 3x minus 2x squared, all to the third power. Okay, so why don't we think of this as u of x, or just plain u, sometimes we call it, is 3x minus 2x squared. And u prime of x, which is just another name for du dx, is 3 minus 4x. So according to this rule, f prime of x will be, as you can see, n, this is n, 3x minus 2x squared to the second power times 3 minus 4x. So you can consolidate that into I left out the square inside. Yeah, see, that one's going to take a lot of practice. But once we've done it, once you've done enough of these, just you don't really need a lot of just first of all, you have to recognize it when you're using the general power rule. And secondly, you have to remember how to work it. So like a lot of these cases, after you've done a few of these examples, you'll find it to be pretty straightforward once you get used to it. Now here they're trying to give us a few tricks for maybe making things a little easier on ourselves. Um, much easier this is. All right, well, let's use that. Let's do the simplifying the derivative of a quotient. All right, let's see what this is all about. So once again, we have, I'm going to write this as f of x over g of x. And we know that from the quotient rule, this is going to give us k. So the only thing though is that calculating g prime of x will require the chain. That's really what is going to complicate this whole thing. So f of x is x. F prime of x is of course 1. G of x is this denominator. So I'm going to write it as oh, actually, no, I'm sorry. It's the negative. I almost missed that. Negative. So let's analyze this real fast. We need g prime of x. How do we do that? So let's try this approach. So we've been doing it like this with the chain rule. Let's be consistent with our notation here. So y equals u to the minus 1/3. Okay. So we also know then that u dx is 2x and dy du is minus 1/3 u to the minus 2/3. Okay, because you're subtracting one from the exponent. So g prime of x is therefore, remember, dy dx equals dy du dx. You're going to have minus 1/3 u to the minus 2/3 times 2x. Okay. And then you're going to have, you can consolidate these two, minus 2x over 3. And then the u itself, remember, was x squared plus 4. So that's g prime of x. So now all of this gets plugged back into the rule, the quotient rule, that is. Wow. Luckily, that's the only messy one. So we know that g of x is x squared plus 4 to the minus 1/3 power. Well, actually, there's no way I have enough room here. Let me move this down. Um, so again, g of x is x squared plus 4 to the minus 1/3. Prime of x is 1. Okay, that's easy. F of x is x. Well, that's easy. And then we have this mess on our hands, g prime of x is 2x over 3, x squared plus 4 to the minus 2/3. Um, oh, and then we still have to divide by g of x squared. All right, g of x is this thing, my x squared plus 4. All right, well, you know what, I do see there's a common factor, kind of. Yeah, you know what, we'll just leave it like this. We could be here all night rearranging it algebraically, but this is it. So the only reason this was such a mess is because g prime of x requires the chain rule, and the result is very messy. Other than that, it's exactly like any other example of the quotient rule that we've ever seen. I think with their, no, all right. Well, they're kind of, they've consolidated it all into this, but we have the right answer. Oh, now this one's kind of interesting because the entire expression is squared. So that this is actually going to be another job for the chain rule, so to speak. So if we think of this as u, Then y is u squared. Dy u is 2u. Here's the challenging part. Um, du dx is going to require the quotient rule, which, if you remember, all right. So what does that tell us? We're going to have x squared plus 3 times 3 minus 3x minus 1 times 2x. Okay. So therefore, we'll end up with 2u times all of this. Right? And then we just have to make the substitution for u, and we're all set. Remember, u is this original ratio here. And finally, we're done. And, I'm guessing, of course, there are probably ways of simplifying it a little bit. Let's see what they did. Yeah, they did consolidate a little bit, but I mean, this is certainly the right answer. And then they multiplied these together to get x squared plus 3 to the third power. Okay. So, all right, anyway, trig functions. Now, the trig functions, of course, also may require the chain rule if we're trying to take the derivative of not just x itself, but a function of x. So in the notation here, the u is understood to be a function of x. Okay. So the only real difference you can see here, they've got, for example, the derivative of sine u is cosine u prime. Now remember, u prime is just another way of expressing du dx. So, and so they're all the same. In other words, if you look at the original derivatives, like we have in this chart, the x's are replaced with u's, but then we need the chain rule. So this one, for example, is all right. So they're all extended in the exact same way. So like I said, most calculus books, when you have a chart like this, they're going to use u's instead of x's, and that's the reason to make it more general. So let's see, do they have any examples? Yes, they do. Here's sine 2x. So if we think of u as 2x, that means that y is the sine of u, and dy du is cosine u. And so we bring these together. And we end up with cosine u times 2. And there we go. Okay, how about this one? Cosine x minus one. Now, you might not be obvious that that requires the chain rule. Oh, but it does. Remember, with the cosine and the sine, the derivative of the cosine is the sign, negative sign. Okay, so we combine these together. Um, I know what happened. I wrote the wrong thing here. This is dy. I was wondering what happened to my dy du. Okay, minus sine u times one. Oh, no, what did I do? I copied the wrong thing. It's getting late, you can tell. That's all right, that's better. Wonderful. All right. Are there any more? All right, there's one more. Let's do this one more, and then we can we'll carry on next time. All right, y equals tangent 3x. U equals 3x. U dx is 3. Y is tangent u. So yes, if you remember the derivative of the tangent, we have the chart right here, is the secant squared. So dy dx, dy du, u dx. Dy du is secant squared x, u rather, and then 3. Right. So then I think here they're simply going to summarize all these rules. Although if you notice they're using different notation, again, this is like there's often many different ways of explaining the same thing in calculus. Just be aware when they're looking at this that they're using in this case. I guess I figure it'll be easier to remember it this way. The u is being used instead of f of x. The v is taking the place of g of x. U prime is u prime of x. E prime is g prime of x. Okay. And now, of course, yeah. So okay. So we'll get back to this, but so far we've actually done wow. We've done all of these, haven't we? Wow. Oh my God. All right. Well, like I said, we'll probably need to get some more practice with these. Let's see what's coming up. The trig functions. Oh, and we'll get some practice. This is 2.4. So um, let's see what 2.5 is real fast. Oh God, implicit differentiation. Yeah, yeah, we definitely want to save this for next time. Um, yeah, you'll see why when we start doing it. So yes, all right. So anyway, so I think we've all had enough. So we'll pick it up next time with implicit differentiation, and we'll see what that's all about. All right. So I'll see you next time.